In this video, we will do a variety of problems involving similarity, congruence, and proof. So in the first problem, we've got this parallelogram shown, and we've got some expressions here. AE is t plus 2. So you know what, instead of t, I'm going to use x because my t's look a little bit too much like plus signs. So I'm going to use x instead of t. So AE, I'm going to put, that's going to be x plus 2. CE is 3x minus 14. So this is CE, so this is 3x minus 14. Alright, and then we've also have an expression for DE, but I guess I'll go ahead and write that down. So I'll do that in a different color. DE is 2x plus 8. Now, I put these two in blue because these are the same length. These are two halves of the same diagonal, so these two should be equal. I put this one in a different color because this is a different diagonal, so this will not equal the other two. So, since these two equal each other, the two blue ones, I can make an equation out of it. So I can say 3x minus 14 is equal to x plus 2. So I'm going to solve this equation by first subtracting x from both sides. So that's going to give me 2x minus 14 is equal to 2. And then next I'm going to add 14 to both sides. So that's going to give me 2x is equal to 16. Next I'm going to divide both sides by 2. So that's going to give me x equals 8. So what are they asking me? What is the length of line segment DB? Okay, so line segment DB is this entire segment right here. So that's what we're supposed to find. Now, notice that we have line segment DE is 2x plus 8. So I know that DE is the 2x plus 8. But now I know that x is 8. So that means that this is 2 times 8 plus 8. So that's 16 plus 8. So that's 24. So that tells me that DE is length 24. Notice, so I'll put a little 24 here. Notice that DE is half of this thing. Alright, so DE is 24. That means EB would also be 24. So that means that segment DB, which is the entire thing, should be double that. 24 plus 24. That is 48. So this should be the length of DB. Okay, this problem is very similar. These two parts of the diagonal should be equal to each other. So the 2x minus 7 should equal the x plus 4. Alright, they're two halves of the same diagonal. So I should be able to solve this for x, but that will not be my final answer, so be careful. So I will solve this by subtracting x from both sides. That will leave me with x minus 7 is equal to 4. I will then add 7 to both sides to get x by itself. So that will leave me with x is equal to 11. Now, what are they asking me to find? What is CY? Alright, so they're asking me to find this right here. Well, he said, changing colors, CY is the expression 2x minus 7. So CY is 2x minus 7. But now we know that x is 11. So I can take this 11 and put it in right here. So that's 2 times 11 minus 7. So that's 22 minus 7. So that's 15. Okay, that's why the answer is 15. Alright, look at this picture. This time they're just asking us for the actual value of the variable. Now, which of these should be equal to each other? I'm hoping you can see that this one should be equal to this one, because these are opposite sides of a parallelogram. So this side of the parallelogram and this side of the parallelogram should be equal to each other. They should not equal CD, which is shorter. But anyway, we don't need that. Let's just make our equation out of these two, which should equal each other. So 10r minus 20 should equal 6r. What am I going to do? Normally I would subtract 6r from both sides. Okay, maybe I'll do it anyway. Students get confused when you subtract away the only thing that's there. That messes them up. Just remember that if you subtract 6r minus 6r is 0. So just put a 0 there. Some students will just forget to do that, and then that messes them up. Anyway, 10r minus 6r is 4r. So now I have 4r minus 20 is equal to 0. Now I'm going to add 20 to both sides. So that's going to give me 4r is equal to 20. And then now I'm going to divide both sides by 4. And that's going to give me r is equal to 5. So there's your answer right there. Okay, which of these best explains why all equilateral triangles are similar? So first of all, an equilateral triangle is a triangle that has 3 equal sides. So let's say that this had sides length 3, 3, and 3. That would be an equilateral triangle. And then let's say I had another equilateral triangle that was 5, 5, and 5. These would automatically be similar, but why? Okay, so let's go through and see which of these things are true. All equilateral triangles can be mapped onto each other using dilations. That is true, except depending on how the triangles are positioned, you might need something in addition to a dilation. A dilation just means it's like you're doing a projection, and you're making one of the triangles bigger or smaller. So for example, if I did a dilation and I blew up the small triangle into the big triangle, then that would be a dilation, and boom, that could be done. However, when I drew these two triangles, I sort of drew them with all of their sides already parallel. What if I had drawn the blue triangle crooked a little? Alright, so see how this bottom side right here is flat? Imagine that I did not draw it so that it was already flat. Okay, imagine I drew it like this. What did I say this was? 3, 3, and 3. Okay, so now I would not only have to do a dilation and make this bigger, but I would also need to do some type of a rotation to get it, angled in the right direction so all the sides would be parallel again. So this first option is close, but not quite, because sometimes you need more than just a dilation. Okay, that was close though, but not quite. All equilateral triangles can be mapped onto each other using rigid transformations. Well, rigid transformations are things like translations, where you just slide it over, or like a rotation. But that's obviously wrong. because some equilateral triangles are big and some are small. So just a rigid transformation where you're not changing the side lengths will not map, for example, this triangle onto the other triangle. So that's no good. That's no good. All equilateral triangles can be mapped onto each other using combinations of dilations and rigid translations. Well, that's going to be your answer right there. Based on everything I've already said, in this example right here, we would need a dilation to make it bigger, and we'd also need a rotation to make it face the right way. So yeah, this is true. All equilateral triangles are congruent. Well, that's false. See how this one's big and this one's small? They're not congruent. Just that's one example. So that's definitely false. All right, so it's got to be the third one. All right, in this problem, they're just asking us to find the scale factor of this dilation. So I'm going to call the scale factor k for a minute. And the scale factor can be found by taking a new length and dividing by the old length. So let's see. Let's look at f prime g prime. That is a new length. So let's see. That is 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's a new length. And the corresponding length, fg, is 2. So that means the scale factor is 4. So this is going to be your answer right here. Don't get confused and say 1/4 because that would mean you were doing old over new. Okay, and that's backwards. Think about it. You know that the one with the primes, that's supposed to be the new image. So we're going from small to big. So the scale factor has to be bigger than 1 then. If it's going to increase everything, the scale factor means it's 4 times as big. If you were going from a big picture like this to a smaller picture like this, all right, then you would expect the scale factor to be something more like 1/4 or 1/8 because it's getting smaller. All right, anyway, this should be the answer. All right, so in your notes, which I'm sure you're taking, make sure you write down new over old.